In this video, we're going to take a look at dynamics of uniform circular motion. So we're going to take what we talked about in kinematics and dynamics in linear motion and apply those to objects that are in motion about a circle. To start here, we need to define uniform circular motion. So anytime we say an object is in uniform circular motion, we mean that it is traveling at a constant speed on a circular path. Now the key here is that the speed is constant, but because we're in a circular path, we're constantly changing direction. So velocity is not constant, just the speed is. The magnitude of the velocity is constant, but the direction is always changing. So if an object is traveling in uniform circular motion, it's going in a circular path with a constant speed, and we say that the time that it takes, we call the period, the time that it takes for it to travel around the circle once, we use a capital T, and that is the period of the circular motion. So using a little bit of our geometry and what we know about the average speed, we can say that 2 pi r divided by the period gives us our speed. Now, where does this 2 pi r come from? That is the circumference of a circle. So this is just essentially the distance divided by the time to give us our average speed. So let's look at an example here of a tire balancing machine. And the wheel of a car has a radius of 0.29 meters and is being rotated at 830 revolutions per minute on a tire balancing machine. So one of the things we need to understand is what is this 830 revolutions per minute representing? And so what that's telling us is that every minute that goes by, this thing goes around in a circle 830 times. And so we want to determine the speed at which the outer edge of the wheel is moving. So we need to use that equation that we just had on the last slide and figure out the radius of our rotation here, as well as the period. And so we look at, well, revolutions per minute. If we reciprocate that, that gives us minute per revolution. So we get 1.2 times 10 to the negative third minutes per revolution. And if we convert that, that's 0.072 seconds for our period. So that's how many seconds we have per revolution, which is our period. That's the big T in our equation. And then at that point, it just becomes, well, what is our circumference? That's 2 pi times the radius of 0.29 divided by the 0.72, and we get 25 meters per second as the speed of the outer edge of this tire. As mentioned before, in uniform circular motion, the speed is constant, but the direction of the velocity is not constant. We're constantly changing our direction. And so if our velocity is changing, that means there has to be an acceleration. And so if we look at this diagram here and see that, well, our velocity is always going to be tangent to the path or tangent to the circle. And so, or in other words, you can look at it is it's perpendicular to the radius of curvature here. So if we draw a radius to the center of our circular path, our velocity has to be perpendicular to that radius, which is also tangent to the path. If we examine our radius vector at 2 different times, at some initial time and some final time, then we can examine the change in the velocity. Now we know the magnitude is not going to change, but we do have a change in our direction. And so by putting those 2 vectors pictured over here at t naught and t, so some initial time and some final time, when we put them tail to tail, we see we have a delta v vector, and that is the direction of our change in velocity. What we're going to do next here is really calculus, but I'm going to talk about it with a little bit of algebra and geometry. And so you don't necessarily know how we get this end result. The key is you need to know the end result and how to use the end result. But I want to show you that I'm not just pulling this equation out of thin air. We have this triangle over here on the left that I'm just going to call triangle 1. And we got that from taking our 2 velocity vectors, and it's at some angle theta, and delta v is going to be the side opposite our angle theta. And if we examine the same circular path but look at the position here, we have a radius as our 2 legs, and then they make an angle theta. And on the other end, we have our arc length. Now, how do we find that arc length? Well, that's just our path. That's a distance, and we can find that distance by multiplying the speed at which we're moving times the time that it takes to get from O to P. And if theta is small enough, okay, if we bring theta to a very small angle, this is where the calculus idea comes in. But if that's small enough, then this is essentially a line, or it's at least close enough to a line to say that, you know what, this is a triangle, so I'm going to call it triangle 2. So I have triangle 1, triangle 2, and hey, they're isosceles triangles with the same angle, so they're similar triangles. This is the geometry part. So if they're similar triangles, then I can do a proportion with these and say that delta V divided by V, which is my leg over here. So if I take delta V, the side opposite theta, divided by the other side, V, and I can set that equal to doing the same thing on the other triangle that's similar, taking the side that's opposite theta, dividing it by one of the other legs right here, and I get this equation that delta V over V is equal to V delta T over R. Now, you might ask, well, why would I want to do that? Well, the reason I want to do that, I know if I find delta V over delta T, that is my acceleration. And so I just rearrange these equations a little bit to get delta T over on the left and get the V over on the right, and I end up with my acceleration is equal to V squared over R. And we give this acceleration name, we call it centripetal acceleration. And so this is an important formula that you're going to need to be able to use when we talk about this circular motion. This is centripetal acceleration, and to find it, we take the constant speed that we're moving around the circle, square it, and divide by the radius. And so what this should tell you is that the faster you're going, the higher the acceleration. Or the smaller the circle, the higher the acceleration. And that should make intuitive sense. Now, that's this equation here is for the magnitude of the centripetal acceleration, but the direction of the centripetal acceleration is always toward the center of the circle. It's in the same direction as the change in velocity. The change in velocity is directed toward the center of the circle. Therefore, we have the acceleration pointed towards the center of the circle. Let's consider this conceptual example here. And we've talked about this before, and we can treat this with Newton's first law to answer the question. But it states that an object in uniform circular motion, and at some point O, it is released from the circular path. And we want to know, does the object move along a straight path between O and A, or does it move along the circular path between O and P? And we know, based on Newton's first law and the law of inertia, that once this thing is released and there's nothing holding it in its path, then it's going to move in a linear path in the direction that it was moving at that moment. And at that moment, it has a tangent velocity, or it has a tangential velocity that is tangent to the curve, or in this case, it's a circular curve. And so we're going to move straight to point A once we are released from the circle. Now let's look at an example that deals with some numbers here and calculating the centripetal acceleration. So we have a bobsled track that turns with radii of 33 meters and 24 meters. And we want to find the centripetal acceleration at each of the turn for a speed of 34 meters per second. And we want to express this as multiples of g. So how big is this compared to the acceleration of gravity? So if we have our initial speed, we have the radius, we can calculate both of those centripetal accelerations by simply plugging them into our equation of v squared over r. And so for the big radius, we have 35 meters per second squared, which is about 3.6 g. And for the smaller radius, we have 48 meters per second squared, which is just under 5g. And that should make sense. On the tighter curves, we know we're going to have a bigger acceleration. And we've experienced that before. Turning in a car or on a roller coaster, when you have a big curve, you feel a little bit of an acceleration. But if you have a real tight curve, you're going to feel much more of an acceleration. Anytime there is an acceleration, we can obviously bring in Newton's second law, and the sum of the forces acting on an object is equal to its mass times acceleration. So therefore, its acceleration is the net force divided by the mass. And this also tells us that the acceleration is in the same direction as the net force. Therefore, we can apply it to circular motion, and so the centripetal force is going to then equal the mass times v squared over r. Now, this is what's very important and is a lot of times a misconception when dealing with circular motion. The centripetal force is not a force that we put on a free body diagram like gravity. All right, the centripetal force is a force that's already there, but is causing the centripetal acceleration. And so it's not a new force that we're now going to start putting on our diagrams. There are forces that are already there. It's the forces that are causing the circular motion that we will then tag as the centripetal force, saying, hey, wait a minute, this is the force that's pushing towards the center. It's causing the circular path, so therefore it is the centripetal force, and we can say it's mv squared over r. A great example of that is this boy spinning a toy airplane on a string, and this airplane's going in a circular path. And so there's a tension force that is coming in towards the center that's causing this airplane to stay in a circular path. So if we were to draw a free body diagram of the airplane, in the horizontal direction, it has tension. Tension is pulling it towards the center. Well, we know that that is the only force that is pushing towards the center on this airplane. So we can say that that force is the centripetal acceleration. We can set it equal to mv squared over r, use our numbers that we have to say that the magnitude of that tension has to be 19 newtons because this thing's moving with 19 meters per second, and there is a radius of 17 meters. If we were to increase this speed, then that would increase the centripetal force, which in this case, the centripetal force is the tension. If we were to decrease the speed, it would then decrease the centripetal force. All right, same thing. We can affect it by changing the radius. The bigger the radius, the smaller the force. The smaller the radius, bigger the force.